A fast-moving object the size of Manhattan is hurtling towards our solar system.
What if an interstellar object whirling through our solar system is actually a nuclear-powered spacecraft sent by aliens to test how humans respond?
NASA is on high alert after 3i Atlas suddenly slowed down by 300%, something they say no natural object should be able to do.
Across the dark expanse beyond Jupiter's orbit, an object from another star has become the center of one of the strangest rumors in modern astronomy. Videos, headlines, and social media posts have exploded with the claim that the interstellar visitor 3i Atlas has just reduced its speed by 300%. Is that even possible, though? And what really is happening? Well, this is one galactic journey you can't miss. You will be shocked. The third interstellar visitor. On the first day of July 2025, the Asteroid Terrestrial Impact Last Alert System, better known as ATLAS, operating from its southern survey station in Chile, detected a faint, fast-moving point of light crossing the star field of Sagittarius. Automated processing flagged it as an unusual near-Sun object, but subsequent orbital calculations revealed something extraordinary. Its trajectory was not elliptical, nor even parabolic, but hyperbolic. This means that it was unbound to the Sun, moving too quickly to have originated within the solar system. Within days, the International Astronomical Union's Minor Planet Center confirmed its status as an interstellar body and named it 3i Atlas. This placed it after Oumuamua, detected in 2017, and 2i Borisov, found in 2019. At the time of its discovery, the comet's apparent magnitude was approximately +18, faint enough to require long exposure imaging, yet bright enough to allow rapid astrometric tracking. Early calculations by the Jet Propulsion Laboratory's Horizon system indicated that it was inbound toward the inner solar system on a steep, retrograde path inclined about 54 degrees relative to the ecliptic. Its hyperbolic excess velocity, meaning the speed it would retain even after escaping the Sun's gravity, was measured near 26 kilometers per second. When combined with solar acceleration, the total inbound speed reached close to 60 kilometers per second, or about 130,000 miles per hour, relative to the Sun. This makes it one of the fastest natural bodies ever recorded in our planetary region. But wait, the unusual part doesn't end here. There's a lot more to this interstellar visitor of ours. 3i Atlas is expected to reach perihelion, its closest point to the Sun, sometime in December 2025, at a distance of about 0.8 astronomical units, or roughly 120 million kilometers. Its trajectory projected that its nearest distance to Earth would be around 1.8 astronomical units, almost twice the span between the Earth and the Sun, meaning it posed no risk of impact or significant gravitational perturbation. The confirmation of 3i Atlas's interstellar nature ignited a rapid observational campaign from the world's leading observatories. The Hubble Space Telescope, despite its aging optics, captured ultraviolet spectra of the object within weeks of its detection, revealing strong emission from hydroxyl radicals, a clear signature of water vapor breaking apart under solar ultraviolet radiation. Ground-based instruments such as the Very Large Telescope in Chile and the Keck Observatory in Hawaii confirmed the presence of carbon monoxide and carbon dioxide in the escaping gas, identifying it as a volatile-rich body similar in composition to long-period comets native to the outer Oort cloud. The James Webb Space Telescope followed up with infrared spectroscopy in August 2025, obtaining unprecedented detail of the molecule-rich coma. Webb's data showed emission bands of water ice, carbon monoxide, carbon dioxide, and organic compounds, all radiating from an active surface being heated as it neared the Sun. These observations indicated that 3i Atlas was far from inert. Rather than being a passive rock like Oumuamua, it was an energetic, classic comet whose activity rivaled or exceeded that of typical solar system comets of comparable size. NASA's Planetary Science Division reported that the object was releasing water vapor at a rate comparable to a terrestrial fire hose, expelling an estimated 500 kilograms of water per second at its most active phases. For a nucleus estimated to be only a few kilometers across, that rate was among the highest ever measured. Spectroscopic analysis provided further clues to its origin. The ratio of carbon monoxide to carbon dioxide was measured at roughly 1.2 to 1, higher than the typical solar system average, suggesting formation in an extremely cold region, perhaps the outer disk of a distant stellar nursery, beyond 30 astronomical units from its host star. The relative abundances of deuterium in its water molecules also differed from known solar system values. All of this means that 3I Atlas was not merely passing through, it carried within it a chemical record of a planetary system light years away. Determining the comet's physical scale proved more difficult. Its brightness fluctuated without gassing, and the coma's opacity made direct imaging of the solid nucleus impossible. By comparing reflected sunlight and dust production rates, researchers derived a probable nucleus diameter ranging from 0.3 kilometers at minimum to 5.6 kilometers at maximum. The uncertainty stemmed largely from the uncertain albedo, or how reflective the surface was. If the nucleus was dark and carbon-rich, it would need to be larger to produce the observed brightness. If it was icy and reflective, it could be smaller. A separate mass estimate, derived from gas flow models and non-gravitational acceleration data, proposed a total mass on the order of 3.3 billion metric tons. Though large, that figure remains tentative and depends on assumptions about density and internal porosity, which are not yet directly measurable. The comet's trajectory continued to refine as additional astrometric data came in. By late August 2025, NASA's Jet Propulsion Laboratory had reduced uncertainties in its orbital elements by a factor of 10. The refined orbit confirmed a hyperbolic eccentricity of about 1.17. This means that its path was open and it would never return. NASA continued to monitor it via multiple instruments. The Hubble Space Telescope provided ultraviolet spectra of photo-dissociated hydrogen and oxygen, allowing the determination of water production rates. The James Webb Space Telescope continued collecting near and mid-infrared data to trace organic molecules and dust emission. Meanwhile, radar facilities like the Deep Space Network's Goldstone antenna attempted, though with limited success, to detect radar echoes that could reveal size and rotation. The Lowell Observatory and Pan-STARRS contributed photometric light curves that hinted at a slow rotational period, perhaps 12 to 15 hours, but these results remain preliminary. The international interest extended beyond NASA. The European Space Agency's Comet Interceptor team, originally scheduled to launch in 2029 to target a future long-period comet, examined whether a theoretical trajectory adjustment could ever allow a spacecraft to intercept an interstellar object like 3I Atlas. They concluded that with current propulsion technology, interception at the required velocity, over 50 kilometers per second, was infeasible without many years of lead time. Nonetheless, the appearance of a third interstellar body renewed discussion about developing rapid response missions capable of chasing future arrivals. The scientific importance of 3I Atlas lies in its chemistry as much as its motion. Each interstellar object provides a direct sample of matter from another stellar system. Laboratory analysis of its light offers clues to planetary formation processes beyond the Sun's reach. Spectra showing elevated carbon monoxide fractions imply that the comet's ice is formed under lower temperatures than those typical in the solar nebula, likely below 25 Kelvin. This suggests that its home system may have been a colder, perhaps dimmer star or a region of a protoplanetary disk far beyond any giant planet equivalent. The detection of complex hydrocarbons within its coma supports the idea that organic chemistry is widespread in interstellar environments, potentially seeding young planetary systems with prebiotic compounds. When it rounds the Sun and begins its outbound journey in early 2026, it will gradually fade from view, accelerating toward the outer solar system and eventually beyond the heliopause. At that point, it will once again become a wanderer between stars, carrying traces of the Sun's dust on its surface. Scientists expect to track it until at least mid-2026, after which it will be too faint for even the largest telescopes.